Hello everyone, and welcome back to Chapter 4. In the previous two videos, we saw how we could take the information from Chapter 2 and apply that to two-dimensional kinematic systems. Basically, we just took the information about all of the vectors in our system, broke them up into their components, and then we used that information in one-dimensional kinematic problems. So basically we've just doubled the amount of work that we have to do in terms of the calculations and the math. But then once we get all of the information from our one-dimensional cases, we can put those back together using the trig to reconstruct the two-dimensional vectors. And so what we want to do today, continuing with this Chapter 4 material, we want to continue the idea of moving in two dimensions, but now we want to apply it to circular motion. And the nice thing about this circular motion is that we want it to be uniform circular motion. And that term uniform is going to mean that something has to remain uniform or constant or the same throughout our travel around this circle. And there's actually going to be more than one thing in this discussion that remains uniform. The first thing that we need to remain uniform is the radius of the circle. Otherwise, if we don't have a uniform radius, then we don't have a circle. We have an ellipse or some other kind of strange shape. The second thing that we want to remain constant as we travel around this circle is the speed. And I specifically use that word speed because as we travel around the circle, the direction in which we travel changes. And so we could call this the velocity. So we'll have to consider that we have a point or a particle that is traveling around the edge of this circle. And as that particle travels, its velocity continuously has to change direction in order to maintain on the path of that circle. But even though the direction of the velocity is constantly changing, it is possible to keep the magnitude of that velocity constant. And so that's what we're going to do, and we're going to give that the name of speed. But we're going to continue using the letter V, only now we're going to abandon the arrow hat on top. So this indicates that we're only using the magnitude of the velocity. And the last thing that we're going to have in this picture, because we have a changing velocity, so any change in velocity, whether it's a numerical change or a change in direction, it's still a change in velocity. And so if we look at how that change in velocity occurs with respect to time, then that means that there is an acceleration in this system. And what we want to do is we want to find out where that acceleration is pointing and what its value is. And as it turns out, the only way that we are going to be able to continuously turn in a circle is if we continuously have an acceleration that is pulling us towards the center of that circle. And so we're going to give this particular acceleration a subscript we're going to call this A sub c, which stands for centripetal acceleration. And if we break down the word centripetal, the first half of the word centri, meaning center, and then petal, if you think like the petals of a flower, where do all of the petals originate from? Well, they originate from the center. And so centripetal, if we were to break down the true meaning of that word, what it really refers to is center seeking. So this is a center seeking acceleration, and we can see that by looking at the direction of all of those acceleration arrows that we've drawn. All of them are pointing towards the center of the circle. And this is also going to be a term that we want to be uniform. So there are three terms here: the radius, the speed, and the acceleration. And we need to see how these three are going to fit together in a mathematical expression. And so to do that, we're going to walk ourselves through a derivation or a proof. So if you want to sit back and watch, you do not need to worry about reproducing these derivations, but once we get to the end result and we have the equation, that's when we're expected to pick it up and start doing the physics. So I'm going to draw that again a little bit bigger. So we'll start with a circle, and just to help us out, I'm going to insert a reference frame with the origin of the reference frame at the center of the circle. And then I'll put in a point on the circle for us to take measurements from. So obviously the first thing that we would consider measuring would be the radius of this circle. So that point is a radius of r from the center, and that radius can be considered a vector. So if I wanted to put in a little arrow hat there, I could. So I now have a vector. And that radius vector, I could describe it one of two ways. I could use the magnitude of the radius and whatever angle it happens to be making with one of the axes, or I could describe it using its components in the x and y direction. And we're actually going to do both. There's no reason we can't describe this vector both ways. So there's an angle theta with respect to the x-axis. But then we have x and y components of that radius vector. And I'm gonna take this point on the surface of our circle here. I'm going to call that point P. And the reason I want to do that is so that I can give these x and y components of the radius vector a name. So these will be the x and y components of the position vector that we're using. And if I add together x of p and y of p, I produce the vector r. But all of this information is unique to the current location of point P. The next thing that we're going to do is we're going to allow point P to start traveling around the circle. So now we will have a velocity vector, And yes, you heard correct, that is a velocity vector because it is currently pointing in a given direction. And there's no reason that I can't still work with just the magnitude of that velocity vector, but at this particular location, since that velocity vector has a direction, we may as well take advantage of that information. And what this means for us is that the velocity vector will have x and y components, just like the position vector did. And let's see. Well, there's one more thing that I would like to have as a part of that velocity right triangle that we've just produced, and that would be some information about the angles inside. Now, I know that there's a right angle between the x and the y components. That's a given. But as far as the other angles within that triangle, if I could get some information about one of those, then I can relate the x and y components to the magnitude of that velocity vector, which is really my goal. If I can relate things to the magnitude, all the better. So here's how we're going to do that. If we look back at our radius vector, so I'm just going to sort of trace the radius vector here, and if we just allow it to continue out a ways, the only reason I'm drawing this is so that we can see the extension of that line. We know that given the direction that the radius vector is pointing compared to the velocity vector, there's actually a 90-degree angle here. And that's because our velocity vector is going to be pointing tangent to the surface of this circle. And so if I'm already using up 90 degrees of the 180 degrees that is made up by this line, that means that the remaining portion also has to be 90 degrees. Okay, so we're getting into geometry now, but let's consider what the geometry can do for us. In the right triangle that we have here for the radius, I have theta and a right angle, which is right here, and then we have some other angle up here which I'm going to call phi, and whatever phi is, it's just the difference in 90 and theta. But now if we go back to our days in geometry, if you'll remember, the angles of opposite vertices have to be the same. And so that angle that I'm getting, sometimes that eraser function takes away too much. So the angle that I'm getting just below that y component of my velocity vector, that's also phi. But if we remember what we said just a moment ago, everything over here has to be 90 degrees, and so phi and 90 degrees, the difference in those is just theta. So this is just a quick reminder of how our geometry is going to help us essentially map out what's happening inside these vector problems. So I now have the same angle theta in both of these right triangles, and that's a really powerful, helpful bit of math, because if I have the same angles in each of these triangles, I now have a way of sort of transitioning between the math involved with those two triangles. And so here's what we're going to do with that. That's basically just been the setup for this problem that we want to do. And we said that our goal is to combine all three of these terms together into a single expression. I want the magnitude of the radius, I want the magnitude of the velocity, and then I need some expression for acceleration. Okay, well, acceleration, as we said, was going to be the change in velocity with respect to time. So let's look at what we have for our velocity vector. We'll start there. Our velocity vector is currently made up of x and y components. And those we can see right now in the diagram. But that information is not very helpful. All we know is that we have an x and y component. And to make matters worse, once we start traveling around the circle, these x and y components are constantly going to be changing as we go around the circle. They're going to get larger and smaller. They're going to get positive and negative as we transfer into different quadrants of the circle. And so it would be much more beneficial if I could represent these components using the angle, which is something we can do now. We have theta, and we can see that as we travel around the circle with theta, not only will the x and y components of position change, but so will the x and y components of our velocity vector. So that's going to be our first step. We want to see what the x and y components of our velocity vector are going to be. So we'll look at our velocity triangle there. And this is kind of interesting. The y component of this particular triangle is the adjacent leg. And the adjacent leg utilizes cosine. In a lot of our vector problems, we have seen cosine associated with the x component, but we do not want to become complacent with how we're doing our work. We have to keep in mind that it is the placement of the angle in the triangle that defines what trig function we should be using. So that y component is going to be defined as the magnitude of the velocity times the cosine of the angle theta, and that means the x component, which is the leg opposite of our angle, we'll be using sine of theta. So there's our first substitution. I'm going to replace v of x with v sine theta. I'll replace v of y with v cosine theta. And to remind everyone, these components, we need to keep track of what direction they're in, so we're going to bring in the I hat, j hat, notation. And the next thing that we notice about this, or that we should notice, is that each term has the magnitude of the velocity attached to it. And so that's something that could be factored out, which we'll go ahead and do right now. So all I'm doing is factoring out the magnitude of the velocity. We still have our sine-cosine relationship in there. But another thing that I want to bring our attention to is given the placement of vector p, if we look at the components of our velocity vector, you'll notice that the x component is currently negative and the y component is positive. Now this actually isn't going to be much of an issue for us in the long run, but just to be consistent with our vector math, we should introduce a minus sign on all of those x components. Later on, as we move through this circle, the sign on these components is constantly going to shift back and forth from positive to negative. So again, that's where I say it's not going to matter in the long run, but we don't want to get too sloppy with our math. So I'll bring that minus sign in there. Okay, next thing, now that I have the magnitude of the velocity in the expression, so we're a third of the way there. Oops. So we've got the velocity in there. Let's see what we can do about introducing the radius into our expression. Well, everything in this expression is concerning the velocity vector. If I want to get the radius in there, then I have to switch over to the triangle with the radius in it. But I can do that now because I have sine and cosine identifying the x and y components of my velocity vectors, but sine and cosine of theta could also be used to identify components of that radius triangle that we have. So looking at the radius triangle, what is the definition of sine theta in terms of that radius triangle? Well, sine of theta is opposite over hypotenuse. The leg opposite of that angle is y of p. The hypotenuse is r. The definition of cosine with respect to the r triangle is adjacent leg over hypotenuse. And so we can come into our velocity expression and we can rewrite sine and cosine as the ratios of those legs from the radius triangle. So here we go. We have negative sine, so negative, and then sine is y of p over r I hat, plus cosine is x of p over r j hat. Now this is where things can get a little confusing, because I now have essentially the x component of my velocity being defined using a y component of position. And I have the y component of my velocity being defined using the x component of position. So does that mean that we did something wrong? Well, no. If we go back and check all of our math, the trig is correct. But keep in mind that as we continue going around in this circle, we're constantly going to be interchanging plus signs with minus signs, and at some point x components will become y components and back again. And so don't let this concern you too much just yet. let's continue with what we have. The goal of this particular step was to get the radius of the circle as a part of this expression, and we've succeeded in that. Both terms inside the parentheses now have r in the denominator. So we'll factor that out. We'll bring that out to the front. And we still have this sort of crazy combination of, y component in the x direction, x component in the y direction. But again, don't let that concern you too much just yet. We're gonna push through. And the next thing you might think is, well, if we could replace x and y components of velocity with terms relating to theta, can't we do the same thing with the x and y components of position? And the answer would be yes, you can, except the only thing that you're going to accomplish is basically stepping back in the math, and we don't want to do that. So we've kind of exhausted what the trig can do for us at this point. So let's consider moving on to finding what the acceleration for this constantly changing velocity expression is going to be. Except I don't want to use that expression. If you remember, delta t is too big. Anything bigger than 0 is going to be too big. And so I would prefer to shrink that down to an infinitesimal interval. And what that means is we can use calculus. So we want to apply a derivative with respect to t to everything that we see there so that we can get an acceleration expression. So obviously dv dt is going to produce acceleration, and what we do to one side we have to do to the other. Now v and r, those are constants, and they will just come along for the ride. So I'm going to pull those two out front, which means that the only thing left that we can take a derivative with respect to are the changing x and y components of our moving particle. So as our particle starts to move around the circle, those x and y components are going to start changing with respect to time. But there's a definition hiding in there. What do we call it when we have a change in position with respect to time? Well, any change in position with respect to time is velocity. And so that means the first derivative that we just took, this was a change in position along the y-axis specifically, and so what we're going to get out of that derivative, still got the minus sign out front, is the y component of the velocity. We still have that pesky I hat there confusing us, but again, hold on. Over here we have the x component of velocity in the j hat direction. And, well, having a y component in the x direction and an x component in the y direction, that's still way too confusing for me. So let's try what we did way back at the very beginning. Let's take those x and y components of our velocity and let's substitute them for the magnitude and angle. Alright, we have a minus sign in front of the y component of our velocity. So now we've, forgive the pun, but we've come full circle here. We're back to the velocity triangle, and our y component is cosine. We have v cosine theta I hat plus vx. Well, vx, if you remember, is sine of theta with a minus sign in front of it because of the direction that it's pointing. So now we've got another minus sign in here. And it's at this point that I'm going to cut my losses, because if I continue trying to make substitution after substitution, these trig functions are great in being able to transition between the two triangles that we've had up here, but we're eventually going to exhaust what the trig can do for us. So we'll clean this up as best we can. We once again have terms that both have the magnitude of the velocity, so we can factor out another v. We now have v squared over r. And then we're left with negative cosine theta I hat plus a negative sine theta j hat. And now those don't look so confusing anymore. And these are technically the x and y components of our acceleration vector. If we put everything together, this is what we get for the components of our acceleration vector. And either way, however you want to write it, it's the same expression. This one up here is a little cleaner, but this now will describe the components of our acceleration vector at any point along the journey. So at any theta value, we will find that we have a, let's see what color, I haven't used that might work, I'll try orange. What we'll find is that we have an acceleration vector that is pointing directly towards the center of our circle. And as theta changes, as we travel around the circle, that acceleration vector will change accordingly to point towards the center of the circle. But I'm not so concerned with the direction that the centripetal acceleration is pointing, because I already know it's already going to be pointing towards the center. It doesn't matter where I am. If I'm right there, okay, there's my acceleration vector. It's pointing towards the center of the circle. If I'm over here, well, there's the acceleration vector. It's pointing towards the center. I really don't need all of this fancy trigonometry to tell me what direction that acceleration vector is pointing. I'm more or less just interested in knowing what the magnitude of that acceleration is. And so we'll go ahead and put the subscript in there, because this is the centripetal acceleration. So now I want to know the magnitude. And so your brain should be singing magnitude mantra, which is square root of the sum of the squares of the components. So this is what we have in front of us. We have the x component and the y component of our centripetal acceleration vector. So we're going to put these into our square root of the sum of the squares expression, v squared over r cosine theta, v squared over r sine theta. We have to square each of these, and so when we do that, now we're squaring a negative quantity, so that becomes positive. We're squaring everything within the quotient there, which gives us v to the fourth over r squared, and then we're squaring the cosine, which will just be cosine squared. And then likewise we're going to step through and square everything in the second parenthesis set, which gives us v to the fourth over r squared sine squared theta. Cleanup time, v to the fourth over r squared can be factored out of each term. And now we're left with everybody's favorite trig identity, sine squared plus cosine squared, which equals 1. And so all that's left is for us to take the square root of this quotient, v to the fourth over r squared, which is now going to be v squared over r. And so we now have the magnitude of our centripetal acceleration. Centripetal acceleration magnitude is v squared over r. And that's it. That's the end result of, probably close to, I don't know what it's been now, 30-40 minutes of setting up the trig and the geometry so that we could do this derivation. But to get to such a nice final result, we can now start doing some physics problems with this. And we're going to actually revisit this expression quite often throughout the rest of the semester, because every now and then we may find ourselves moving in a circle, or it doesn't even have to be a full circle. We could be moving through a circular arc. And so whenever that happens, there will be a centripetal acceleration resulting. So now on to an example problem. So for the example problem, we'll come right over here. So at some point, most kids dream of wanting to be an astronaut. And to be an astronaut, you not only have to be really good at your math and your physics, but you also have to go through quite a bit of physical endurance training. And so one of those is basically a human centrifuge, where they'll put a potential astronaut candidate in a chair, which is attached to a boom arm. And maybe this boom arm is about 10 meters long. And then they turn this on and it starts swinging around in a circle. So if we were to look at an overhead view, so this would be the front view of what's happening. And then an overhead view, you have the boom arm over here with the astronaut inside of it. and they're going to turn it on and start moving this astronaut through a circle. And so the radius of the boom arm will remain constant, but there's really nothing that says that we have to keep the velocity or the speed constant. We can slow this up, or not slow it up, slow it down or speed it up. But in any case, as long as this boom arm is moving, then the potential astronaut is going to be experiencing a centripetal force. So we have that center-seeking force. And so what we can do by varying the speed of this apparatus is we can increase or decrease that acceleration. And what we're doing here is we're testing the individual's endurance to extreme forces of acceleration. So we call these G-force, and we'll get to the definition of force in the next chapter, but for right now we're just going to focus on acceleration. So what we refer to here are the G's that this person is exposed to. And so the centripetal acceleration will be expressed as some scalar integer of the acceleration due to gravity. And a passing score for most of these is about 9 G's. So 9 times the acceleration due to gravity. So how fast do we have to get these astronaut candidates moving if they want to pass this test? Well, we'll take our expression for centripetal acceleration and we'll plug in 9 G's for the value of the acceleration. So 9 G's is going to be 9 times the value of gravity. So we're getting really close to about 100, just a little bit shy. This is going to be about 88.3 meters per second squared. And so just to give you an idea of what this would feel like, you're basically going to feel like you're 9 times heavier than what you currently are. So if your weight increased by a factor of 9, how do you think that would affect your ability to function? And my guess is that none of us would be able to function. But all right, so there's our expression. And we're solving for the necessary speed, so we'll go ahead and rearrange our expression to solve for v. To do that, I would need to multiply over by r and then take a square root. And for any root, we have the potential of there being a plus minus, and we might think, well, we're just talking about the magnitude of the speed here, so we can throw away that minus sign. But that minus sign actually plays a part in our diagram here, because not only can we achieve this 9 G's worth of acceleration by moving this direction, but we could also achieve it by moving that direction if we wanted. So the direction, we can go clockwise or counterclockwise, but we'll go ahead and just we'll work with the positive. We'll stick with the magnitude here. So we have 9 times g, which we already calculated up there, times the radius. All that needs to go into our calculator. And then we'll take a square root, and we get a speed of approximately 29.7 meters per second. So there's going to be somebody else in a room over here with their hand on the dial, cranking up the dial, making this thing go faster and faster and faster until they reach this velocity, causing them to travel around in the circle again and again and again. And if they can reach that velocity on the dial, then that means that they've accomplished the goal. They've gotten to 9 Gs, and so they pass the test. But then they don't stop there. They turn up the speed some more, and they turn it up some more, and some more, and some more. So why are they doing this? Well, if we increase the speed, we're going to increase the centripetal acceleration. And so now this has become a true test of endurance. What they want to know now is just how much centripetal acceleration can this person take. And so you may have numerous candidates who want to be a pilot on the next space mission, and candidate number 1 passes with 9.2 Gs before they pass out. So technically they passed because they got up to 9 Gs, but then they passed out at 9.2. And candidate 2 makes it up to 10.1 Gs. Candidate 3 makes it up to 11.5 Gs. Candidate 4 didn't make it. They passed out before reaching 9. So candidate 4 is out, but the first 3 candidates all passed the test. So technically they could all be the pilot on the next mission, but which one would you want piloting the ship? Well, you would probably want to pick the person with the highest endurance, just in case, because not every contingency can be planned for. But if there was a some case scenario where the rocket experienced a centripetal acceleration of 10.3 Gs, even if it was just momentarily, well, these first 2 candidates are probably going to pass out as a result. And you don't want the person that's flying the rocket or the ship to be passed out while they're trying to pilot the ship. So you're probably going to let this person sit in the pilot seat. Alright, so what else could we do? What else can we do with this centripetal motion stuff? Really anything involving circular motion. So we have our radius r, we have a speed of v, and we have centripetal acceleration. One thing that I did want to mention, back here where we said it doesn't matter if we go clockwise or counterclockwise, at least for the math it doesn't, but what about for the person? What do you think? Would it matter if they were, I'm going to draw a little seat here for the person that's in our human centrifuge. So in one case scenario, the person could be moving forwards, and in another case scenario we could be moving the person backwards. And in both cases there would be some center-seeking acceleration as our test subject goes around in a circle. So would it matter the direction that this person is traveling in terms of how many G's they can experience before they pass out? And as it turns out, people that are accelerated backwards have a tendency to pass out sooner than the people that are accelerated forwards. And there's a reason for that, and it's more of a physiological reason than anything else. If we zoom in on this person's head, you got your eyes and your nose up here and your mouth, and you got your brain in here. So as you move forward and you continue to move forward, you continue to accelerate forward, well, what happens to all the blood in your brain? Well, it ends up sloshing back to the back of your brain. And it's the back of your brain where you have all of basically the critical life support functions that the brain takes care of. And so you can stay conscious for a while, but you're stealing blood away from the front of your brain, which is where a lot of your cognitive functions are taking place. So you'll stay awake longer, but you'll basically be drooling and you won't be able to function so much. Whereas if you travel backwards, so now we're going to travel backwards. So we're going to travel, come on, here we go. So now we travel backwards. Well, so now the opposite happens. We see all the blood rush to the front of your brain. And so your cognitive functions, they're probably going to be through the roof. But now you've lost a considerable amount of blood back here, where all of those critical life support functions are happening, and so you're probably going to end up losing consciousness much faster as a result. So this is why when we do put our astronauts in the rockets, we'll draw ourselves a rocket here, we have the astronauts basically laying on their back in the rocket, so that when they accelerate forward, all the blood is going to rush to the back of their brain and keep them conscious for as long as possible. And then they'll actually go through cognitive training to make sure that they can still function for everything that they need to do during their mission, at least during liftoff. And then everybody else who's along for the ride back here, they might pass out during the trip, either from these kinds of effects or just flat out excitement and anxiety. But so that's the description of our centripetal acceleration. In the next video, we're going to take a look at relative motion. And with relative motion, basically everything is going to be the same, except we're going to see what happens when one person tries to measure the motion of an object with respect to one frame of reference, and another person tries to measure the same object from a different frame of reference. It's the same object moving through space, and so the rate of change of position, the rate at which it changes velocity, the rate at which it accelerates, it should all be the same, but how do we compare those values from two different points of measurement. So that's what we need to figure out in that next video. Alright, so signing off, and we'll see you then.